Lesson 9, Optimizer Join Operations. So after completing this lesson, you should be able to describe the SQL operations for joins, list the possible access paths that we can use for joins. Okay, and in this lesson, we're having a look at the join methods. And we document 3 that are commonly used as a join method. It's the nested loop, and we've talked about these briefly. We're going to fill in the details and formalize our discussion on them. First one is the nested loop, the second one is the sort merge, and the third one is the hash join. We'll also add a 4th one that is technically viable and is used in some cases, but it's fairly rare to actually use a Cartesian join. There's very few applications that can actually use it and return meaningful data. Okay, and then we're going to get into the details of the join operations. Before we get into details, what I like to do is do a quick overview of this on the boards, and then we'll get into the details of the slides. That is a relatively short number of slides. So I'm going to move over to the board. And we're going to take a look at this example. I have 2 tables, my 2 favorite tables. T1. T1 has a number of columns on it. All of the columns would have data, but for this discussion, what I'm really focusing on is the columns that I'm going to use as my join condition to join my columns, okay? So in T1, we're going to use column CN. It can have up to 1,000 columns. I just picked one. I just gave them sort of random names. And what I'm going to use is CN to join with other table. And my other table is T2. It has a group of columns. And I'm going to pick one of those to join with. Once again, I'm not really interested in the name, just as long as they're a column that has equivalent data that makes sense joining. Perhaps in a realistic example, this is in the employees table and this is the department table. And this is the department number in the employees table and the department number in the department table. It's a primary key here. It's a foreign key here. But in my case, I just gave them generic names. I have some data, and generally off a disk, the data is randomized. Okay, and I only have a few rows because we don't want to be here all day having a look at this example. But the data is randomized. And there's a number of ways of contemplating how to do this query. One of the ways, we could want to use the data the way it's on the disk right now and just do it as a form of a loop. In reality, the optimizer actually won't do this because it tends to be a very expensive way of implementing a join condition. But in theory, we can talk about it. And then we'll talk about the one case it does use it for the Cartesian product. What I could do is read the first row here, and I'll just put a little marker beside it to indicate this is the row we've read on this side. And then I can read a row on the other side. And I can compare and if I'm doing an equal join between these 2 tables, I compare to see if the values are the same. If they are, it should be included in my output. So these are the same values. I put it in the output. Okay. Then I've got to advance the rows. So these are unsorted. So what I need to do is read the second row of the second table and compare them. Are they equal? Nope. Read the next row. Are they equal? Nope. Read the next row. Are they equal? Nope. Read the next row. Are they equal? No. 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 Okay, so for this row, I had to do effectively, which is logically a full table scan on the other side. Okay, then I can advance this side. Okay, compare this, and I start reading over again. I need to read this one. Are they equal? No, 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 no. There is no match for 1. So there's no output from that. And then I start over again. Read this one. And then I start doing my checking. Read this one, the match. No, 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 no. Oh, found a match. We're going to include that in the output. Read this one and read this one. Then we go to this one, do the same thing. No, 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 no. Take the 5. Yes, I found a match. Include it. Okay? But there is one case that has duplicates, so I need to know if there's any other 5s. In my examples up to now, I haven't had any duplicate data, but there may be, so I still have to keep reading. Match, no, 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 no. There was only 1 5. Grab 3. Match, no, no, no. Yes, we found the match. Include it, but check to see if there's any more. I still have to read to the end because this one happens to have a 3 at the end included in the results set. Okay. Next time I have to read this one and check this one. No, yes. Included in the results set. No, 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 no. And I'm done. Now, why doesn't the optimizer want to do this? The main reason was if we have m rows in this table and n in this table, we multiply it by that. As the tables get bigger, the number of reads we have to do get really large. And sometimes we can read a few rows in a block, but sometimes we've got to look at other blocks. It causes us more reads generally. Okay, there is one case where the optimizer will actually use this. So we'll just erase this really quickly. And the case is a Cartesian cross product. In a Cartesian cross product, I don't have any join predicate. It's not an equal join. And I'm just taking T1, join it with T2. So I take every row out of the first one and I join it with every row out of the second one. Okay. Then I read the second one and I join it with every row out of the second one. I do this. And I just keep going until I do all of them. In that case, I have to produce m times n outputs, so I do m times n reads. Now, there is one optimization we did put in. Okay, it would be more efficient if we could read a smaller one of the two totally into memory, using the sort area size as a temporary buffer, spill it over to disk, so we have it in memory as much as possible into memory, and then read the other one to join it. Then we could probe the one in memory, and it will actually reduce the number of reads overall we need to do, especially if I can get a large sort area size to do it. But the only time it reads both sides and join all the rows is a Cartesian cross product. And if we actually think about what it's telling us for a practical application, if this is the employee table and this is the department, what the Cartesian cross product is saying is every employee works for every department. And that is never true in an organization. I've done Matrimatics. I only worked for one department as a regular solid dotted line. I had another couple of managers I worked on projects with. They were dotted line reports. So even in that case, it wasn't a pure Cartesian cross product. I just had a few people I reported to. So this tends to not return any useful data. So we really don't want to do that. Is there a more efficient way to do a join? Well, of course there is, or we wouldn't have multiple join methods. So except for Cartesian cross products, we don't like this sort of processing. So let's look at another case. What happens if we sort the data on both sides? Can we get a more efficient processing? So I'm going to move to the other board and take a look at the example. In this case, I have the original data, and then I've sorted it, so this becomes the sort order for the first one. And this is the one I'm interested in joining. I had the data regularly randomly, and then I sorted it, and I get the data in this order. Once it's sorted, it's a very efficient algorithm, okay? I read the first row, and once it's sorted, I don't really need this data. I can get rid of it. I'm just working with the sorted copy. Then what I can do is read this one, and then read this one and see if there's a match. So I'm working with this one and this one. Okay, if there's a match, I include it in the output. If there's not a match, such as this case, what I want to do is advance the smaller one, read this one. Now I find a match included in my output. Okay, so this is the last one I read here, this one. And what I need to do is advance one of them, okay? And what it generally does is advance the one you just read. The theory being, if there are a bunch of things in a block, we may be able to get the next row out of the block of data. That way it's sorted without doing another read. And now it compares this value with this one, doesn't match. Is one smaller than the other? Read that side, so read this one. We find the match, include it, okay? Now we need to advance one of them, so we advance this one, okay? It's the same value, it's a match. Now we just read this one, we now read this one, read that one. Now it doesn't match. Which one is the smaller side? It's the one over here. On T1 with the 3, read this one. Now we find another match. Now we need to read one of them. We'll read the smaller one. Does it match? Nope, sorry. Advance the small one, we have a match. Okay, now we would advance this side, okay, because it has a match. Okay, now we need to advance one of them. It doesn't really matter. Advance the 6, okay, and then check it. It doesn't match. Advance the 7. Well, this one is smaller. Read this one. We're at the end of the table. We know there are no matches for these two. We don't even have to worry about them. Once one of them hits the end of file because it becomes as big as this, then we're done. If there were ones that would match, there was another 6, we would have found the 6. And we eventually, one side will run out of data sometimes before the other. This is once it's sorted, this is quite an efficient algorithm. It's really doing M plus M reads to merge the two together, and we sort of walk between them, merging them together. So it's a reasonably efficient algorithm. The problem with this method, if it's small amount of data, it looks pretty good. I could sort it in memory. If this massive amount of data, the sort becomes very expensive. So the larger the data is, the more expensive the sort is, the less desirable it looks. And that, okay, looks desirable for large tables. One way that can reduce the cost, if I can find the index and do either a range scan or a full scan, that will return the data sorted on one or both sides, it can potentially reduce the cost. The other way is a previous step provides it sorted. So if this is the sort merge operation, we sort it both sides first and then merge them. If we have large volumes of data, we don't want to do it. Is there a way we can do it with large volumes of data without sorting the data? And the answer is yes. So I'm going to move back to the original board, do a little bit of cleanup on it, okay, and we're going to talk about it. Now, in this case, what happens if we had an index on C1? Okay, so I'll build just a little index. I won't make it very big, but just to give you a little idea. My crude indexes. If we have an index on C1, so I'll just point a little arrow back and forth. Whoops. My arrows aren't very good today. Okay, then what we could do is read through this table the way it is on disk without sorting it. Just read the first row and then use that first row to probe the index. Find here, walk the tree structure. And if we have a match, there will be a row ID that points to a row. In this case, it will point to this row. Okay. Since if there were duplicate values here, there's 2 3s. For the entry 3, there's just going to be 2 row IDs pointing to them. I didn't put them in the right order. Perhaps it's a reverse key index. Who knows? I was just drawing them. So we take a value, probe it. If we get one or more row IDs, we include the output. In this case, we just got 1. Take this one, probe it, and we return no row IDs, we just skip it, read over the next one. Take this one, read it, probe the index, and we find this one. We walk through the index that leads us to here, retrieve the row, and join it in the output. Look for number 6, no match. Okay, look for number 5, that's the one that returns 1, we already did it. We would just join this one with this one. Okay, probe for 3 and we find the 2 of them. Okay, and include both of them in the output. We just return the 2 rows from the table and then we just have the data to join together. Take 2, probe it, and we find this row and join it together. Okay, by having an index, we don't have to do any sorts. And it's quite efficient to probe the index on that side. Okay? So this is essentially a nested loop with an index on one side. We do a full table on this side and scan the index on the other side. The nested loop without an index is like the Cartesian cross product, and it just won't do it logically. Is there another way of doing it if we don't have the indexes? Of course there is. Let's get rid of the index and talk about how, once I clean it up, how we might do it without an index. Okay? What we could do is find if one of them are smaller and build a hash table. So I'm going to take a moment, build my hash table quick. So the hash table is just a structure that uses a hash function. I can read through the table, take each of the keys for the column that I want to do the equal join on it, and hash it to a location in the hash table. So I just take a key, apply a mathematical function as a hash function, take the key as the input, and it will give me a slot. So we'll put some slots in the table. So perhaps 5 will hash to this location. And each of these has a row ID associated with them. I'll just call it row ID 1. Okay, so we have the 7 row IDs. When I hash it to this location, I don't actually need to store the key because it was always hashed to the same location. It's a repeatable hash. But I put it in to illustrate it. And we store the row ID. So now I'm just going to go ahead and fill in the values and talk about them. So okay, so I went and filled them in. I discovered there was 2 5s. I guess I should have made my table a little bigger. We would just document the 2 rows. And I just applied the hash function to each of these, and they hash to different locations. And I fill in 1 or more row IDs. And to do this, we have to do the full table scan, and then we build the hash table. And we build it in memory. If it needs to, it will spill over to disk. Okay, we'll actually partition it if it has to fill over to disk. It uses the sort area, the hash area size in memory, and it will spill over to the temp table space if it needs to. Once I have it built, then it's actually more efficient than an index, because an index has generally for large tables multiple levels. So as things come in and out, I may have to reread some of the nodes or read them in initially into the cache. This is once it's built, if it's in memory, it's a pure calculation. I read this row and I hash it, and it hashes to the same memory location. And I look up the 2 row IDs in the original table, row ID number 1, and include it in the output. And I look up row ID number 5, included in the output. Then I read 2, I hash it, it tells me I'm joining that with row ID number 7, which is this one down here, so I put the 2 2s in the output. So probing the hash index, once it's built, is very efficient. It's just a calculation and check if there's any row IDs. If they are, bring them up. If there happens to be something in this table that's not in this table, I like 8 and 7, I just never probe for them. So once the hash table is built, a very efficient way, it can only do equal joins. There are some limitations, and it requires a full table scan on at least one side. Or if we could find a filter with limit it, we could limit the subset of the rows using an index on one or both sides. So that gives you a little overview of the 4 join methods that we're going to talk about in this. The Cartesian cross product, the sort merge, the hash join, and the nested loops. Now I'm going to move back to the terminal. Now we're going to proceed and have a look at the slides in here. So how does the query optimizer executes the join statement? It considers a number of factors. What's the best access path for particular tables? Can I use an index? Should I use a full table scan? Okay, what is the best join method for the volume of data and the type of join I'm actually do influences it? And what's the best join order that I should use? So it looks at all of them to decide what the best way of doing it is. So join methods. Join defines the relationship between 2 row sources. It's a method of combining data back together because we did a third normal form and removed repeating groups. Now when we query, we have to put things back together. Is controlled by join predicates, which defines how the objects are related. And these are our 4 join methods. 3 of them are used practically in applications. Cartesian cross products don't show up very often. There are a few things they can actually solve. I've seen a couple in applications, and there's a couple of uses of them in the data dictionary, interesting enough. Okay, so this is just looking at a query using the new join syntax. We're joining D to E, and I really like the new joining. We either use the using to indicate which column is comma, we document the join condition, or we use the on to specify different columns on both sides if they happen to have different names. And then everything else in the where clause is actually filters, okay, that are reducing the data further. They're not the join condition. The using in this case is the join condition. So that is the join condition, and then we have the non or additional filters, non-join predicates or additional filter predicates. I find it's a little nicer syntax to read than the older style that we use, but we support both and people get used to both of them. Okay, this is an example of using the nested loop. Where the driving source is scanned. Quite often it's a full table scan. Sometimes we can use an index on the left side to reduce the data to make it more efficient. Each row in the driving table is looked up in the inner, and it usually uses an index scan on the inner to access it. At the minimum, do full table scan on the outer and an index scan on the inner to run it, as I showed on the board. So in this case, we're using the join the employees to the department. Okay, on condition is department number is the same on both tables, and this is additional filter that we can use. So it does a nested loop. Okay, it's doing a table access by department, by index row ID, and we found an index. We're using the unique scan. We're doing a full table scan on the larger table and probing the other one because we didn't have an appropriate index. Normally on the department number, this is the primary key, so it will have a unique index on it. This one is a foreign key. Unless you put it on, it doesn't have an index automatically. In some cases, it may be a good idea. It may give us actually a better access path for the nested loop. But in this case, we didn't, so it used it, the larger table, as the driving table. Okay, there are actually 3 implementations of the nested loop. The first one was available as the original implementation. Okay, that was available since we implemented it. And then we came up with this one, and this, the prefetched, which is an optimization, was introduced in 9i Release 2. So the first one is available all the time. If you're on 9i Release 2 or later, this is also available. It's really just a nested loop. But now what we do is that when we look up the rows, what we find is the data in the index is scattered badly compared to where the data is stored on the index. So batching up a group of rows and accessing them makes an easier way. And how they indicate this, we still do a nested loop, but normally with the previous implementation, we have an index scan followed immediately by an index access in the execution plan. In this case, we put the index range scan to batch up a group of them, but then we indicate the probe by those row IDs later. What we're just doing is batching up a bunch of probes to decrease the probability we need to reread rows. So we show an index scan and a full table scan of the other ones, but we have to, once we do the range scan, we have to probe the table using the row IDs. We just moved it above to indicate that we did a little optimization to batch up the row access. Probe it a number of times for a number of keys from the full table scan instead of just probing it for one. Tends to optimize, reduce the number of rereads we have to do in some cases. In 11G, we added a further optimization. So this time we're joining 3 tables. We're joining them using the new syntax. We're doing a join of employees to department, okay, with an on condition, and then a additional filter, and then we're joining it to the we're just joining the 2 tables, okay. Now it still is a nested loop, it's just a further optimization, okay. What we want to do is that there are possibly 2 indexes available. And once again, we have the concerns, so they document this as a double nested loop, but they actually have 2 indexes that are available. They're logically joining the 2 indexes together and then using the rejoined as a virtual table to probe the other table. So they treat it as logically a double nested loop. So join the indexes together as one nested loop and then join that result to the other table. And it's still a nested loop, just a further optimization to try to reduce the number of rereads we need to do. And in 11G and beyond, the optimizer can pick what it feels is the best of the 3 optimizations. They're still all nested loops.